I'll continue talking about the processes shaping evolution of stars and gas and galaxies today, mostly talking about still one process that underlies the entire hierarchy of processes, gravity. And I'll continue with what I left off yesterday, talking about mass accretion histories of galaxies, but hopefully also getting to some interesting calculation that we can do with simplest bare bones galaxy formation model, where we can get to actually what baryons are doing, not just dark matter, what gas is doing, and even what stars are, how stars are forming. So today, I hope that there'll be time to talk about two parts: finish the mass assembly histories of collapsed objects. In particular, yesterday I already showed you how halos collapse and how their mass of the main progenitor grows. Some of you may have tried the exercise to play with these things extracted from simulations and a simple approximation. Today I'll focus on origin, so trying to understand why the mass assembly history is the way it is, why simulations show us a particular mass accretion history. And then we'll use that result to provide the basis for the matter accretion rate for galaxy formation model, which will provide the mass budget for the baryons that will control how much gas is available for forming galaxy and so on. Right, so we left off yesterday talking about mass accretion history. Let me zoom in a little bit so you can see the entire figure. So this is just a repeat of a slide showing how a mass assembly history of a halo like this is assembled or constructed using numerical simulation. At each redshift, a peak is identified that contains most of the particles associated with the final object. The mass is measured within a given radius, enclosing a density contrast. In this case, the choice will be 200 relative to the mean density. And then at each redshift, this is done for the main progenitor, for the largest object, which contains most particles, and mass is recorded. So then we have mass as a function of time, and that's called mass assembly history of such halo, or MAH. I showed you, and maybe you saw in the exercise, that this is how they look like for simulated halos, in this case, for objects that end up with total mass of about 10 to the 12 that reaches 0, which is close to the Milky Way's mass. And again, these two panels just show the same thing. Left panel shows in log-log plot, log mass, log time. Right panel, log mass, but log linear plot, so that the time here is linear, and you can clearly see the two regimes, the fast accretion regime and the slow accretion regime, that is very characteristic of these assembly histories regardless of the mass. And we saw that when we look at objects of different mass in these simulations, let's see, yeah. This is sigma that I showed that I'll use, and when we looked, no, guys click too much. Let's see. Yeah. So we saw that if we looked at median, sort of smooth median mass accretion histories of objects of different mass, but normalized here to their final mass, they all have the same characteristic shape. This is log-log. But there is a systematic difference. There's a trend with final mass, with largest objects tending to assemble their mass later. So for example, an frequently used choice is to define a formation time, which is a kind of a thing that you have to choose or semi-arbitrarily here, because the mass assembly is continuous. So if you want to define an epoch, you either have to define a particular time where mass accretion history reaches a particular slope, so where the slope is some value, or for example, where main progenitor reaches a certain fraction of the final mass. So the frequent choice is to choose a half of the final mass. But here you can read off, if we say choose instead definition of formation redshift as an epoch where 10% of the final mass is reached, so it's 0.1. And then there is a line here that you can easily trace, and you can see that if we define formation time this way, then for largest objects, the formation redshift will be formation time would be largest from the Big Bang, so it means that they are latest. They assemble their mass later. So there is a systematic progression from small masses to large masses in the formation time, which is reflected in the systematic change of these curves. And I try to stress, but let me stress again that the main differences, the differences you see here for different masses, the final mass is already rescaled. So the main thing that you see here is a combination of the fact that the objects of different mass have different typical overdensity initially, which is reflected in the fact that RMS fluctuations are a function of scale, and largest objects have smaller typical RMS. So it means that they're at a given time, their typical fluctuation delta will be smaller, right? Because they are all adherent to Gaussian fluctuations. And the typical fluctuation, 1 sigma fluctuation in the Gaussian, which is given here, is smaller on a scale that corresponds to formation of clusters. That's, we saw yesterday that these scales forming cluster-sized objects. And then for galaxies that form in scales here and below, the typical fluctuation time amplitude is several times larger, so that their collapse is facilitated just from that fact. So they galaxies have a head start relative to clusters. But there's two components here. One is amplitude and one is slope, which determines which kind of substructures are collapsing around the main objects and merging with it. And those two factors, so the amplitude and the slope, are combining to create a systematic difference in mass accretion histories. But one thing that I pointed out is that in these rescaled units, if we look at the smallest objects that have the largest mass in the rescaled units, the mass accretion history at a given time is also the shallowest. So it means that m dot is the smallest for smaller mass objects. So their mass is largest, but m dot is smallest, right? So if we take the ratio, we can expect it to show a smaller difference than you see here, just for the mass accretion history. So this is what's shown in a plot here, and so accretion time scale, because this is has units of time, mass unit cancels out, and we have inverse time in the derivative, so the ratio has time units, and so this is a time scale for exponential increase of mass at a given time, and this is the same lines replotted in for this quantity, and we see that the difference here is still visible, but it's smaller. They're all within the factor of 2 or so from each other, right? And so this is why it is, if we want to come up with an approximation for these numerical results, it's useful to work with this quantity because it has smallest variation with the mass of the object. So we can parameterize it in a relatively compact function with a weak dependence on total mass. And then this is the reason why in the literature, some examples of which I given to you, approximations are usually constructed in the form of m dot, which involve mass, but effectively they approximate this ratio, this time scale. Right, and we'll come back to this. So this is a numerical result, but we'll use it to build a galaxy formation model using this accretion rate, right, approximation to it. Okay. So simulations are great. We saw a number of movies already. They show us complexities. They give us reasonably accurate answers. But the question is, how can we understand what's happening in simulations? Is it possible? Anatoly in the morning showed you that a lot of things can be understood with using analytical models such as Zeldovich approximations, right? So the approach I'll take from now on here is similar. So I'll use a simple model in which we'll try to understand why the mass assembly histories of halos that simulations show us are the way they are. I'll show you that you can get pretty close to actually describing simulation results with a relatively simple model, which has a couple of ingredients. But there is also the main qualitative thing that it will show you, in particular, what is the origin of this fast accretion regime and early times in the mass accretion histories and a slow accretion regime at late times, right? So the model we'll use for this is way simpler than what Anatoly was describing, because it turns out that for the purposes of understanding this problem or these simulation results, a relatively simple spherical collapse model already takes you most of the way to this understanding. And then you can refine it if you wish with modification of the assumption of the spherical collapse model. For example, considering collapse of ellipsoids rather than spheres, you can do the same with Zeldovich approximation, but I'll show you how the results change if we go from a spherical collapse to ellipsoidal collapse. So the spherical collapse model for the evolution of perturbations in expanding universe is probably the simplest model of such evolution, because from this model you can also derive a linear model or equation for linear evolution of perturbation that Anatoly was describing yesterday. It assumes spherical symmetry, which immediately reduces a three-dimensional problem, because we're considering evolution of perturbations in 3 dimensions in space, to one-dimensional problem, because now we only have one coordinate, radius, to consider, because everything is spherically symmetric. The second thing that it gives us is the spherical symmetry assumption, is with assumption that mass outside a given radius is distributed uniformly. It gives us ability to use the first Newton's theorem if we consider classical gravity, or its equivalent in GR, the Birkhoff theorem, and neglect effects of matter outside a given radius. So, when we consider collapse of a shell of a given radius, we can forget about outside universe completely, right? Its evolution fully is set by initial conditions that we choose, which will reflect expansion of the universe at that time, at the initial time. But after that, cosmology is forgotten. The shell just collapses according to gravity, according to the mass that is enclosed into inside this radius. So this model has greatly simplifying quality, so it's the simplest thing you can imagine for describing evolution of 3-dimensional perturbations. And of course, you can question it because it's a spherical cow model, so-called. It's a great example of a spherical cow model. It's very simple, and you can question whether its simplicity is actually justified. We saw from numerical simulations that when peaks collapse, they don't have spherical shape. They have substructure. They have structure around this, which is also not homogeneously distributed. So you have all the right to question the use of this model. But to some extent, its validity, or whether how useful it is for us, is in how well it will work, right? So we can try to forge ahead and see what happens, how much it can help us. It's a typical approach to building models. You can start with simple sort of order of magnitude or the simplest analytic estimates and see where they take you. And if they don't take you far enough, as far as you want, you try to build a more complicated model if it's not accurate. That's the approach. It's also the model that is results of which are very frequently encountered in the literature. The quantities such as critical linear overdensity for collapse, the virial overdensity that come up from that model are almost in every paper on subject of galaxy formation. So it's very foundational in terms of background that it provides for the whole field. So one more assumption in this model, so the spherical symmetry and the homogeneous distribution of matter, spherically symmetric distribution of matter that this model makes. Another assumption that we'll make is about density profile, so how densities change. So what I'll assume, and I'll explain why, well, it's already explained there, but we'll talk about it. What I'll assume is that if I deal with a positive perturbations, in other words, if I consider a collapse of a peak, so delta is positive and is peaked at a particular location, the profile, which means that density as a function of enclosed density as a function of radius, within such peak is always increasing towards the center, to a smaller radii. So in other words, if I have two radii, R1 and R2, that is R1 is smaller than R2, the density within R1 will always be larger or equal, at least, to density within R2. So in other words, the density is monotonically increasing with decreasing radius, or at least stays constant, right? The case when density stays constant is a special thing called top hat fluctuation, and you can encounter this term in the literature, and this model is often referred to as the top hat collapse model, although we apply in a spherically symmetric model, the perturbation, the profile itself does not have to stay constant. And as long as this monotonicity assumption is correct, and I can assume this, it simplifies the problem even more, because in this case, the mass enclosed within a given radius can be assumed to stay constant during evolution. And I'll pause here and I'll ask you, why is this so? So why, if I make this assumption, why can I assume that the mass within a given radius, and actually any radius, is constant during evolution? Think about it for a second, a few seconds.
Maybe because there's density inside it. If it's higher, so the shells collapse faster, and no matter what side,
So that's correct, and I'm very pleased to see that you remember, because you heard this a couple of weeks ago. But you also, so it's great that you remember, but you also went through this discussion a couple of weeks ago. Anyone else? Do you guys, probably most of you didn't hear what was said. Did you hear? So give an idea why this assumption follows from this assumption during evolution. So mass within a given radius can be assumed to stay constant as the shells evolve, first with expansion of the universe. So what's going to happen is that because universe expands and initially perturbation is small, initial expansion is very strong. So what will typically happen to radius r, at first it will expand with the universe. Then if perturbation is actually bound and is positive, at some point it will be slowing down. At some point it will slow down to velocity of 0 and will start to collapse. So radius will start to decrease. So at first radius will increase, then the radius will decrease. So radius will evolve with time. But as I said, that with this assumption, throughout that evolution, when I mark a given shell, as the shell evolves, the mass inside of it will stay constant. Is it clear why, or you don't have any idea? Or volunteer? No? I'll give you a hint. Like I said, with the spherical symmetric assumption, I can forget about background universe. The initial expansion is just an initial condition to my perturbation. So as radius evolves, I can think. So for example, what's going to happen when the perturbation reaches the largest radius, at which point a given shell will reach largest radius, at which point it will turn around. So it means that at that time derivative was 0, and r will be maximum over its evolution. So after this moment, the perturbation will collapse, and background universe is irrelevant because according to the first Newton theorem or Birkhoff theorem, it cannot act on spherical perturbation. And therefore, after that, what we're dealing with is just pure gravitational collapse or free fall. The time of free fall is proportional to square root of g over rho density inside this radius. Right? We've seen this before. This is dynamical time, or free fall time. Right? We've seen it before, right? And actually, this follows just from dimensional units. If you take a units of density and g, right, the units of inverse square root of that product is time. That time is dynamical time that characterizes a gravitational system, where gravity is the main force acting on the system. So then, if I deal with a shell that initially has density profile increasing towards the center, increasing with decreasing radius, it means that towards the center, the free fall time is smaller. So the shells evolve faster. The shells with smaller radii evolve on a smaller time scale. So the larger shells will never be able to catch up with them, right? It's actually the opposite when during the expansion before that epoch. And so at any given point, when shells are expanding first and then collapsing first, this monotonicity condition ensures that the shells never cross each other. And so the mass enclosed within the shell stays constant. Is it more clear now? Or is it still unclear? Right? So this is an assumption, but it's a relatively reasonable assumption. If we deal with peak of density, we may reasonably assume that that peak of density is correct at any given radius, right? So the density is increasing towards the center. Okay, so we make this assumption, and then even without solving, the actual evolution is described by differential equation. We'll come back to that. But even without solving any differential equations, we can derive an equation that is surprisingly useful and is worth keeping in mind, and also very easy to come up with, to derive, and so probably easiest to remember if you need to do it yourself. So if mass is constant, we can just designate it to be m, and it will be independent of time for the reasons that I just described. The density within a given radius, when radius evolves, will be just 3m over 4 pi r cubed. We deal with a spherical perturbation. And so we're interested in evolution of overdensity, density within a given radius defined by mean density of the universe, -1. And so we want to derive an equation for this quantity, right? The mean density of the universe evolves like this, mean density at redshift 0, an inverse scale factor, or 1 plus z cubed, because expansion factor is inverse 1 plus z, right? So we can plug it in here, and then we can plug density from here, right? And then collect the terms with a simple algebra, and we'll get this equation. 1 was taken to the left, so I'm taking density from the previous equation, so it was 3m 4 pi rho mean r cubed. Sorry, 3m 4 pi r cubed, and then the evolution of the mean density, which is mean density at redshift 0, divided by a cube, so a cube goes there. And so this ratio, which is 1 plus delta, is then proportional to I cube divided by R cube, A cube by R cube, with this quantity that I already introduced yesterday, but it's usually in the literature is called comoving Lagrangian radius. So it's a scale associated with a perturbation of mass m at some very, very early epoch. Right. Clear? Yeah. Okay, so this is the equation for delta as a function of t, right? And let me rewrite it as a function of the equation for radius. So it's the same equation, just rearranged. This is radius as a function of t with this quantity Lagrangian radius. This is expansion factor, and this is 1 plus delta to minus 1/3 power, because r came in as a cube, so delta will come in as 1/3. Okay, so we have this simple equation, which we can write as for delta or for radius. And let's look at its structure, what it tells us. The first is we can consider delta equals 0, right? So this term is gone, in which case the radius is just evolves as R Lagrangian times the scale factor. But it also tells us, before it goes there, it also tells us that if I take Lagrangian radius here, so I look at dimensionless quantity, so evolution of radius in units of Lagrangian radius of the perturbation, then its evolution is composed of two factors. One is expansion factor, which reflects the expansion rate of the universe. And the second factor is delta. So the evolution of radius of a perturbation is a function of background cosmology, which is of course the same for objects of all masses and all scales, right? This is how universe evolves. So when we consider evolution of objects of different mass, this factor is the same for all of them. This factor is, tells us that the evolution, second thing that affects evolution, is not the initial radius, it's not the initial mass, but it's initial perturbation amplitude, right? Because if I write down this equation at initial time, then at initial time, R initial will be expansion factor at initial time and delta at initial time. So the expansion of the universe at initial time will set this factor, and the overdensity at initial time will set the second factor. And also the only things that then will affect my evolution, background cosmology and the perturbation amplitude with which perturbation started. No mass, no radius, right? So if perturbations on all scales, if sigma as a function of scale was a flat quantity, it had no dependence on scale, objects of different mass would collapse identically. They would have all the same mass accretion histories, right? Because their deltas would be all characteristically the same, distributed with a Gaussian distribution with the same sigma, right? So statistically they would be identical. So when we would plot mass accretion histories of halos, they would still have all the same shape that I showed you for the reasons, because that shape reflects the initial profile, as we'll see. but there would be no systematic difference between them. All lines rescaled for different masses would coincide. So those differences that we see for the mass accretion histories, they all come from the fact that objects on different scales have different typical initial amplitudes of perturbations, right? So when we are looking at mass accretion histories and we're seeing the differences, we're seeing the fact that we live in a lambda CDM universe, which has particular power spectrum that depends on scale, and a characteristic amplitude of perturbations that becomes larger when we go to objects of the small scales. Okay, so that's already pretty useful fundamental thing, that evolution of perturbations just depends on background cosmology and initial fluctuation amplitude. Let's see what other things this equation can tell us. So first of all, when we can set delta to 0 at any given time, so it means that we deal with no perturbation, just mean density of the universe, we get a trivial result that the radius of that region, which has delta of 0, which means it has mean density of the universe, will just evolve as expansion factor, right? You can say, duh, that's what we would expect, but it just means that we didn't make any mistakes deriving this equation. Well, it was difficult to make a mistake because it was just simple algebra and conservation of mass. So no perturbation, region expands just like background cosmology, just modulated by its initial Lagrangian region. So we're taking the initial radius of the perturbation, and then it expands as a universe with expansion factor, right? So that's very trivial, just to maybe a consistency check. But the less trivial result is if we consider, say, a negative perturbation. So delta smaller than 0, but it's bounded on -1, right? So if delta is negative, it means that this quantity, 1 plus delta, is less than 1, right? And in the limit of -1, we would get 0 here, but of course that's an achievable limit because it means there is no matter in a given region, and that's not possible. So this is a hard limit. But we can get to very low values, right? So this number can be arbitrarily small, arbitrarily close to 0, and it comes with a negative power. So it means that we will be dividing this product by numbers smaller than 1, which means that we'll get an answer that is larger than this product, right? Yeah. So what does it mean? It means that if initial perturbation was negative, so delta I was less than 0, the radius at any given time will be larger than this. It means that the perturbation was expanding faster than the average universe would expand from this initial Lagrangian radius. It means that negative perturbation with a negative delta expands faster than the universe. Right? Yeah. Clear? Right? You can think about it as expansion of cosmology with a lower density. So cosmology with a lower density effectively has less gravity, less gravitational pull within a given radius, and it would expand faster than cosmology with a larger density. So when we deal with the spherical perturbation of negative delta, we can think about it as just a different cosmological model with a smaller mean density, which will expand faster than my background cosmology that after initial conditions would not affect it at all. So it will be expanding just like a separate universe. Okay, so regions corresponding to negative perturbations, so less than mean density, will expand faster than universe. And then, of course, if delta is, I'm having trouble with this clicker today. When regions are positive, then the opposite, this number is larger than 1, which means that at any given time, this radius will be smaller than Lagrangian region multiplied by expansion factor, which means that perturbation expands slower than the mean density of the universe, the mean region in the universe. So it's lagging behind the mean expansion. And we can think about it as evolution of the universe with a larger density than the mean. Okay, so that's not complicated, but it's already very useful because it gives us the consequence that within the spherical model, even without solving any differential equations, it tells us that overdense regions will get smaller as the universe expands in terms of their relative fraction, and underdense regions, negative deltas, will get larger because they expand faster than the mean density of the universe. So if we consider a region that expands with the universe, the underdense regions will get larger and larger volume under action of gravity, and overdense region will get smaller and smaller fraction of the volume. So what does it do to the initial PDF of delta, which was Gaussian?
It becomes narrower?
No. If anything, it becomes wider because perturbations grow. But initially, the Gaussian was symmetric. Yesterday, we discussed that it's symmetric function, right? So it describes the probability to have a particular delta around 0. The mean delta is 0. And it's a symmetric PDF, right? So it means that fraction of volume in negative delta and fraction of volume in positive delta is equal. And that's a property of a Gaussian field. And we saw that when we look at the field, it looks right? Realization. So here, under action of gravity, those equations tell us that underdense regions will expand faster than universe, which means that in comoving units, their volume fraction will get larger, while overdense regions will get smaller. So in comoving units, their fraction in overdense regions will get smaller. Right? So will distribution stay symmetric?
No.
Let's take a vote. Who votes yes? Don't be shy. So everybody thinks it's no. Who thinks it's no? The distribution will become asymmetric. Few people, a lot of people are either neutral or don't care. It cannot stay symmetric because two sides of the distribution, to the left of 0, to the negative values, and to the positive, evolve differently. They evolve in opposite directions, right? So the distribution will become skewed. Let me sketch it. If we start with a Gaussian field, so it's PDF as a function of delta. You know, the best I can draw, I'll try to draw it symmetrically. Will be a bell curve, which is symmetric. What gravity will be doing to it is, on the one hand, the deltas will grow. So, in other words, probability to have larger delta will increase. But at the same time, the negative part of that curve will have to be larger because the volume fraction associated with the negative deltas will have to be larger. The distribution will be skewed towards negative values of delta. It will become asymmetric. Or, to simply state it, the distribution will become non-Gaussian. So that's the simple consequence is that gravity will take an initial Gaussian field of perturbations, the delta, it will turn it into a non-Gaussian field, right, immediately. And then how far away from the Gaussian will depend on how long the gravity has a chance to act on the perturbation, right? So when we look at initial Gaussian field, this is the realization I showed you yesterday, and we'll look at the result of a numerical simulation that I also showed you yesterday, which, this came from this. The initial conditions for this box were something like this. Symmetric PDF of delta, equal volume fractions of positive and negative deltas. And this looks like Gaussian noise. It turns into this, which looks anything but noise. So essentially this qualitative process. Large underdense regions evolve faster, so the final distribution is dominant, volume is dominated by underdense voids. And collapsed regions occupy a small fraction, so they turn into dense, bright nodes in this color scheme. Right. So evolution here, again, coming back, looks pretty density field on these scales at this redshift looks still pretty Gaussian. And then as gravity acts on it in these comoving units, you can see that underdense regions are kind of expanding like bubbles and turn into large voids. And this is why, with time, the fraction of volume occupied by voids grows. The second, and actually also why galaxy distribution has so many underdense regions at redshift 0. So this is galaxy distribution around us. We're at 0, 0, and this is a coma cluster, and this so-called CFA Great Wall, a large filamentary or sheet-like structure. But what really is striking in this distribution are the presence of these bubble-like underdense regions. And that's why underdense regions are occupying such a large fraction of the volume, because gravity makes them so. They expand faster than the average universe. So the consequence 2, which is actually kind of consequence of the first consequence is that if we have two nearby underdense regions, they will expand faster than universe, and in comoving units, they will have to run into each other at some point, right? And so you can think about material being swept out of them and into the same direction. So if they are neighboring, then the material will be swept towards each other, and as at the intersection of two bubbles, it will form a sheet-like structure. So even to describe this process properly, you have to consider the collapse model that actually takes anisotropy of collapse, such as Zeldovich approximation or high order approximations. But qualitatively, we can understand formation of such sheet-like structures even from this simple model by knowing that underdense regions will expand into each other. They expand faster than units in comoving units. Their volume will increase. They'll have to run into each other and have to form some sort of wall-like boundary between them. You can see this very clearly in this picture, which shows it's a picture from a galactic Binion Tremaine galactic dynamics books from a paper where a spherical distribution of particles was set up in expanding universe. So this distribution is expanding with within a given cosmology. I think it's omega-1 cosmology. But expansion is taken out, so the evolution is shown in comoving units, right? So this extent of the sphere doesn't change because expansion we took out, but you can probably barely see, but there are perturbations. Most of this distribution is uniform, but in the center there are 3 perturbations that are underdense, that are set up in initial conditions. There are 3 of them, but inside each of them there are also 3 smaller underdensities. And so what you can see is that as time evolves, and it evolves from here to here to here to here to here to here, these underdense regions are increasing. They're spherical, so they're increasing the spheres as bubbles. And at some moment they run into each other. So for example, here the 2 underdense regions are expanding, but they're still not touching. But at some point they start touching, and they form intersections. So they form boundaries between them. That in 3 dimensions would be sheet-like, right? But what you can clearly see here is the volume associated with those underdense regions in comoving units is constantly increasing, right? So at low redshift, you have these structures that look filamentary or sheet-like in 3D, just because these voids are running into each other. Why am I telling you this? Well, this is one of the clues of, as I said, why the large-scale structure is the way it is, why it's dominated by voids in terms of volume, and also by sheet-like structures if we look in 3D in galaxy distribution, but also because we may well be living in one of those sheet-like structures formed by this process, our Milky Way. Because when we look at the distribution of nearby galaxies in the catalog of Kravtsov, which was constructed not so far from here, maybe 100 kilometers, I don't know, at the observatory. The distribution of galaxies looks very asymmetric, and it looks very sheet-like. So if you look at one direction, we just see kind of a quasi-spherical distribution of galaxies with Milky Way somewhere at 0, 0 here. But in some other direction, if we turn it this way, it's very flat. At least majority of galaxies are in very flattened pancake-like structure. And above the distribution and below the distribution are 2 voids. One of them is called local void. The other structure, I don't know, but it's a void. It's underdense region. And so with this process, these voids are expanding and running into each other and forming this sheet-like structure in which our Milky Way finds itself. So again, so we could understand quite a bit just from conservation of mass within this model. So it shows you how useful such model can be for qualitative understanding of what's going on in seemingly complicated 3-dimensional collapse. So it can provide very useful insights, but it's not an equation that we can use to actually tell us the exact evolution, because it's not a full solution. It involves 2 functions, r and delta, a, t just set by cosmology, which we can assume and know from Friedman equations. But r and delta are 2 functions that we do not know, right? And they depend on each other. They are connected through this equation, consequence of conservation of mass. And so in order to say, for me to be able to plot radius as a function of time or delta as a function of time, I actually have to solve the equation. I have to figure out what those 2 functions are separately. And there are several approaches to this. So for example, what we can do is that we can take that equation that was in the previous slide, and we can take first derivative in time and second derivative of time, and linearize the equations that result for those time derivatives. Linearizing means that we neglect any term that is higher than linear power in delta. So anything that looks like delta squared or delta cube, we just remove from the equations. Or if we have a factor like 1 plus delta, we think that this factor is 1. So we neglect delta compared to unity. So this approximation is applicable when delta is much smaller than 1. It's a typical procedure that's used in physics to linearize the equations, such as the linear oscillator equation. Anatoly told you yesterday the result of this solution to this equation is such that the scales and time dependence separate, so that there's only single time dependence in this solution, which applies to all scales together. So all scales evolve at the same rate given by the growth function, so-called, which is designated as d plus because it corresponds only to the growing solution, the part of the solution which grows with time. So usually it's designated as d plus. Which depends on cosmological model, because one of the terms of the equation depends on mean density of the universe, and one of the terms, the friction term, depends on the Hubble constant. You can find the derivation of the linear equation and its solution in the notebook, one of the background notebooks in repository, if you want. I won't go through this, it's pretty basic stuff, but if you want to see how this equation can be turned into equation for linear, in the linear perturbation theory for the perturbation delta and solved, you can look at this, this notebook. The key thing for us is that we'll be using the fact that this model predicts that perturbation on any scale will evolve proportionally to this function of time, the growth function, which for models with omega lambda 0, so without cosmological constant, is actually can be solved numerically. So we know this function in closed form analytically. It has particular simple form for omega 1 universe, where it's just proportional to expansion factor or time to the 2/3 power. But it can also be solved for open cosmology for omega matter 0 less than 1, except that expression becomes much more complicated, but still an analytic expression. For omega lambda non-zero, that function is not obtainable analytically, but we can obtain it by numerical integration or using accurate approximation to it. It doesn't matter. So for any cosmology, we can derive evolution of perturbations as a function of time in this linear model, and it applies to all perturbations of any scale at the same rate. So all scales depend on the same in the same way. And you can see, I told you that expansion of evolution of a perturbation depends both on scale and delta, right? So there is radius and delta here, and the reason this dependence on scale disappears in the linear model is that essentially we're neglecting 1 plus the delta in this 1 plus delta factor, just like linear theory does. Okay, and the omega 1 universe actually the fastest grows. All these functions are such that they at high ratios they behave kind of like this, but then they all slow down in low omega universe, and the fastest growth occurs in omega 1 universe. That's sometimes useful to remember. Okay, and then we'll, like I said, we can, if we make this first assumption of monotonicity of density profile, we can assume that mass is constant, which simplifies equations for the radius. And that equation is very familiar, right? It's just acceleration of an object or a shell in spherical symmetry that is given by mass enclosed within the shell divided by r squared. So it's just a Newton's law, right? And this equation also describes anything that if I throw a pen, right, it exhibits a parabola because mass stays constant. Mass of the Earth doesn't change while this pen is flying, but radius of the pen is changing. So I gave it initial conditions. I threw it up. I gave it some positive kinetic energy, so it had to go up. Then gravity slowed it down. It reached the highest point where velocity was 0, and then it collapsed to whatever radius. For the purposes of this classroom, R0 is the stage, right? Of course, you know, if the same perturbation, if the same equation explains, describes evolution of a shell, then solution will be exactly the same. It will be a parabola, Right? It will be the same function that first increases and then collapses. And the exact form of this solution is not relevant for us, but I'll show it to you. Now, this is for omega lambda that's equal to 0 because there's no force associated with lambda. With lambda, this equation will have a term that corresponds to vacuum energy that has this form, so it's proportional to radius. It comes in as positive, so vacuum energy or dark energy acts as acceleration force, right? So unlike gravity that slows things down, which comes with a negative sign, dark energy comes with a positive sign, so it accelerates things. It first slows down the gravity because it counteracts the negative term, and in the moments when it starts to win over, it accelerates. It creates a positive acceleration. This equation can be solved analytically, of course, because we know it from basic mechanics. This equation in general cannot be solved analytically, but can be solved numerically. It's a simple differential equation. Right. And we'll consider perturbations that collapse. I won't talk about the underdense regions anymore, so positive perturbations. In order for them to collapse by a given time, they have to be bound. So the boundness condition is can be set by initial conditions by considering kinetic energy and potential energy of perturbation at initial time, and we can require it to be less than 0, so that it will be negative. It could be bound. So here's an example of such evolution for perturbation with a particular mass scale in a cosmology that's open, but omega lambda is 0, because in this case this curve is analytic, solution is analytic, so it can be drawn without solving differential equations. And again, it has this form, which is the form that describes evolution of a pen when I threw it. Right? It goes up because initially perturbation was expanding with the universe. Then the gravity of mass enclosed within perturbation slows it down until this moment when velocity is 0, and then it starts to collapse. Because there's no dark energy, this curve is symmetric around the maximum. And from the maximum to the collapse, the time it takes for that perturbation to collapse is actually given by the free fall time that we'll consider, because we're just dealing with a free falling sphere from here to here. Because the curve is symmetric, the entire evolution is given by 2 times the free fall time of the sphere from the peak, right? So we know the time of collapse just from this basic consideration, that it will be 2 free fall times if we use the density at the maximum to compute the free fall time. The dashed line here shows the background factor, expansion factor of the universe in which this was computed. And you can see that at early times the radius was evolving with at a rate close to the expansion factor, but somewhat slower. So at some point this difference, this constant slowing down, became apparent and they separated, right? So expanding universe is doing this perturbation is doing this. If we start with the mass enclosed within the initial radius and evolve it with expansion rate or with this radius, we can figure out what delta is doing because the mass is conserved. So this is a solution. This model provides a solution for radius, and so in that equation it gives us one of the functions, and we can just invert the equation to give us delta as a function of t once we know r as a function of t from this analytic solution of the equation. Is this clear what we are doing?
And 1.5 megaparsecs at which time will be?
This is Lagrangian. This is Lagrangian, so it's just a label. It's essentially this comoving Lagrangian radius at initial time when delta can be set to 0. So it's comoving, so it doesn't matter. But effectively, you can think about perturbation on the time scale.
Asymptotic?
Yeah, asymptotically back to 0. Okay, so delta has this evolution. Again, once we know the solution for r, the equation that relates them gives us delta. And this is how it evolves. At first, the evolution is power law-like. It's a log-log plot, so it's a power law-like. But then it quickly accelerates, and approaching this time when radius goes to 0, the delta goes to infinity, because now we have a mass divided by r cubed, where r goes to 0. And so the ratio goes to infinity, so delta increases. Of course, it cannot go completely to infinity because we'll have deviations from pure spherical symmetry, but it becomes large, right? And the dashed line here, so this lower dashed line, shows us prediction of the equation where if we linearized it, so if the same equation that I described to you, we could derive equation for evolution of delta in linear regime by neglecting higher order delta terms and 1 plus deltas. So this is a prediction of solution of that equation. This is initial delta multiplied by a growth function. And you can see that in the beginning, it does evolve the same way as the actual solution because the linear approximation works. In this regime, deltas are small. And then they separate when the linear approximation starts to break down. But you can see that the difference between the solutions is actually quite small all the way until delta becomes a fraction, a few tenths, right? Even at 1, when delta becomes 1 here, it's still 20–30%. So it's still quite accurate. It's not very far off in terms of what predicts. And then as we get closer to collapse time, of course, the actual density goes to very high values, whereas linear density continues to increase with a close to power law. It only reaches at collapse time, it only reaches value of close to 1.7. So less than 2 here, right, shown by this dashed line. The second line here, the dotted line, shows you what would happen if the same initial perturbation evolved in omega-1 cosmology. Because the growth rate in this cosmology is faster, so the growth function goes faster than in open omega universe. There is more matter to slow down things. So this perturbation would collapse at an earlier time. But as it turned out that when it would collapse, the linear prediction would be still close to this 1.7 factor. So it would still be close to this dashed line. So for any given cosmology, we can actually, let me show you this. For any given cosmology, we can figure out at what over density predicted by linear theory radius reaches value of 0. So in other words, the spherical perturbation collapses. And this linear over density is called critical over density of collapse, designated as delta C. And this is the result of actual calculations for different models, both with non-zero lambda and with 0 lambda, as a function of omega matter at redshift 0. For this factor, essentially resolving the spherical collapse model for different cosmological models and seeing at what extrapolated linear over density from initial one the perturbation collapses. You can see that there is a trend. So there is a trend for different cosmologies. But if we look at the range of values of this factor plotted here, it's very small. For omega-1 cosmology, it's about 1.68. 6.9, so close to it, but somewhat smaller. And then there is a trend as a function of omega, but this trend doesn't, unless omega becomes very, very small and we live in an open universe, we can get as low as 1.6. But in the lambda CDM, you can see that even for low omegas, it's still very close to 1.67. So in other words, for reasonable cosmological models, because dark energy is detected in our universe, we can expect variation of this factor to be around 1.67, 1.69, right? So it can be, for all effective purposes, be assumed to be constant for lambda CDM cosmologies. Why is this factor important? Because according to the spherical collapse model, we know that the perturbation will collapse when initial over density of the perturbation will reach this value. So that's prediction, right? We consider spherical collapse model for a given shell of a given initial R value, but we can do it for any shell. So if we have a perturbation with different deltas within different radii, we do it for different shells and we'll get different collapse times, right? So we can do it for any given shell, and each shell will collapse when it's linearly extrapolated over density from the initial one will reach this value of collapse. That's prediction of a spherical collapse model. There are these growth factors because they tell us how much this perturbation would evolve according to the linear theory. This factor is just to divide it. Initial perturbation is the actual perturbation from which we start. For example, at redshift 1000, that initial perturbation can be 10 to the minus 3 or so. For galaxy scales, it's about 10 to the minus 2 or so. So this is a very small value. If we divide it by the growth factor at that time, it linearly extrapolates this value to redshift 0. And then if then we multiply it by the growth factor at time of collapse, it takes us this whole expression becomes linearly extrapolated over density at the collapse time from that initial one. When this factor is equal to the critical delta, according to this model, the perturbation is collapsing. It corresponds to the collapse T-collapse. Yeah? Is it clear? So we're using the solution, we're seeing what delta linear model predicts us when the solution reaches radius of 0 when it collapses, and we use the result of the spherical collapse calculation that this delta C is almost constant to tell us for a given perturbation at what time it will collapse. This equation is an implicit equation for T-collapse, right? And so if we deal with the perturbation of a given profile, so it has a given initial of a density as a function of radius, for each shell with each given delta, we can figure out using an implicit equation what the collapse time will be, and we can record, okay, here's a shell delta with radius r, and here's its collapse time, and we can do it for every single shell and create a table effectively, right, a function where T-collapse is numerically solved. For omega-1 universe, the solution is completely analytic because the growth factor, as I said, is very simple. Its growth function is just a power law function of time, or just inverse 1 plus z. And we can solve for z-collapse, for example, and we'll get the result from that equation that z-collapse is just delta divided by critical density of collapse minus 1. So it tells us that the reaches of at which each shell collapses just reflect the initial perturbation amplitude, right? And again, if the delta increases with decreasing radius, the smallest radii will collapse first, and then the largest radii will collapse, and will build up the mass of the object as a function of time, right? Of course, this is omega-1 universe. In the for any other cosmology, we'll solve for T-collapse numerically, but the basic fact remains that the sequence of collapse reaches or collapse times just reflects the deltas of the initial shells of the perturbation. So then, if we start with a given initial perturbations with a given profile delta less than Ri, the mass enclosed within this radius is given by this equation, right? So within the sphere. And so we can record for every single shell, we can record its collapse time or collapse reaches. We can record mass within this radius. And this gives us time as a function of mass. It gives us a mass assembly history of this collapsing perturbation according to the spherical collapse model. If we take the derivative, we can get m dot, which we also measured in simulations. So the main point is that the mass accretion history of a collapsing object, according to the spherical collapse model, simply reflects its initial over density profile with a simple factor that's independent of mass, delta C. Okay. So if we know the initial profile, we can predict what the mass assembly history of such profile will be, right? So we deal with, this is a question of what a typical over density profiles around the peaks in the Gaussian field. This is something that can be computed. There is a classic paper by Bardeen et al. 1986 with several other papers. Actually, many papers dealt with this, but here's a couple of representative ones, Ride and Gun 87, and then a very recent one, Dalal et al. 2010. And you can find sort of condensed exposition of the results for how you go from a Gaussian field to computing a typical profile around the peak in one of the background notebooks. I won't go through this here, but effectively you should know that this can be done because the Gaussian field is quite simple mathematically, and we can take its moments, such as sigma, or cross moments, more complicated moments, quite easily. In particular, we can also take conditional probability distributions. So we can compute the mean density profile around the peak as simply looking at the mean conditional density R, conditioned that the peak has some other over density at some other different scale. Actually, I call delta R star here, so in this figure. So this is an example of such calculation. The code to compute this profile you can find in this notebook. If you look at it, or in that background notebook, it's actually duplicated. So this is a result of a calculation of a mean density profile, so delta inside a given radius, under condition that inside some other radius, which is 1 in these units, delta is some value, delta R star, where I set it to be 1.69. I set it to be equal to the delta critical predicted by the spherical collapse model. This is a computation for the such mean profile. Because it's conditioned to have a particular value here, right? It does have this value. You see that's roughly 1.7. And the dispersion, which is shown by the shaded region, becomes 0 because the condition there pins down what the density should be. At all other radii, the profiles are unconstrained, so you see that the dispersion is quite large. In fact, this calculation just allows profiles to actually even go down. Once they satisfy this condition, they can go down or can go up. At larger radii, they can also scatter depending on what's around such peak. But this is a calculation. It's actually an analytical calculation in the sense that we just take it's just written as an integrals. We take them numerically, but there's no differential equations of any kind. No simulations involved. It's just the operation on a Gaussian field. But gives us a mean profile for the delta inside the given radius, which we can use in conjunction with that previous model to compute the mass assembly history. So I'm asking you, what will be the mass assembly history according to this model from a profile like this, from the mean profile? Let me go back to this. Take a look at this this equation. This for omega 1, but it qualitatively still works because actually throughout, at least at redshift, until redshift 3 or 2, omega is close to 1, so this solution is actually close to real 1. And so redshift of time of collapse, corresponding time of collapse, is just the over density within a given radius divided by the constant 1.69 minus 1. So it's effectively just factored initial delta profile. And I'm telling you that this initial profile looks like this, or at least according to assumption that the mean that the initial profile is just a profile that's conditioned in a given R, which ensures that by redshift 0 this shell will collapse because it reaches critical density at 0, which is this profile is extrapolated to redshift 0. So what would mass accretion history look like for a profile like this according to this model? Let me write down the equation again on the board. This is mass enclosed within a given radius given its delta. This is the collapse redshift, which will have corresponding collapse time given by delta. So let's anyone wants to volunteer a guess for what mass assembly history will look like? Let's consider 2 radii, just to make things simple. Let's consider 10 to the minus 2 in these units, which has this delta, 2.2, and 1/10, which also has essentially the same over density because the profile is very flat in this radii, right? So they have, those 2 radii have almost identical deltas. What will be their collapse redshifts according to this model? Don't be shy. There's only one factor here, which is delta. This is effectively constant, right? So if at 2 radii deltas are similar, what will be the collapse times? Wake up, guys. No?
Equivalent. Equivalent.
They will be very equal, yeah, they will be very similar. So if delta is actually equal, the collapse will be equal because that's the only varying factor that comes into this equation. I don't know if they're exactly equal, but they are very similar, right? Means that the collapse will be very similar for these 2 radii. And actually, the collapse of all the shells up to about here will be very similar because delta is almost the same, right? The mass also has R cube factor, and then it also has delta. So as R
as delta stays constant, right, the only factor that's varying as we go from shell to shell is r. And the mass that the shell encloses will vary as r cubed, right, for these various deltas. So mass will grow if we consider shells of increasing radius, but their collapse time will be almost the same. So we can tell that collapse of these shells, the mass assembly history that corresponds to the collapse of these shells, will look like almost a vertical line in the plot of mass versus time, mass versus redshift, right? Then, as delta starts to change, so we go from this radius to this radius, so now with increasing radius, the delta goes down, which means that the Z collapse will become smaller and smaller and smaller, and then the mass will still increase because enclosed mass will always increase, but now the collapse redshift will be stratified in time. So in other words, there will be almost a wall-like regime where mass is increasing vertically, almost at the same time. That corresponds to this part of the profile, and then a stratified regime where the mass will be assembled at different collapse redshifts when the delta will start changing. So here is the actual comparison of this model to the mass accretion histories of halos of 10 to 12, and this is the model that takes this profile and effectively applies that prediction of spherical collapse model to predict the collapse redshift for every shell. We see this vertical regime corresponding to the inner profile, and then we start seeing that instead of still pretty steep, but you can start seeing curvature. So this is a regime where we reach the outer part of the profile where shells start to collapse at different redshifts. Now, what do you think about the model? Does it look good or not? It doesn't look too good, right? But in defense, it did tell us that there should be two regimes. One is very, very fast accretion, right? And then kind of slowing down of accretion. It's something that I was stressing with respect to the mass assembly histories of actual halos, that there is two regimes, rapid accretion. And you can see that in this linear scale, you cannot even see the difference, right? This is steep, this is steep. You see it in logarithmic scale, but not here, right? So this model does predict the fact that there is a steep increase of mass at some early times, then slowing down. But overall, it does not describe the actual mass accretion histories of halos. Why is this so? So what's the difference? Let's go back to how we actually compute the mass assembly histories, and then we'll talk about the model. We can suspect that the model is wrong in two ways. Either the spherical collapse model is incorrect, or that the profile that we assumed for the initial perturbation is somehow deficient. It turns out that both are true, so both the spherical collapse model is not quite correct, but that inaccuracy that's introduced by spherical collapse model is relatively minor, as you'll see. The main problem with the solution that you saw is actually in our computation of the density profile. And to understand what's wrong with that computation is we should go back to how mass assembly history is actually created for the halos. So we track the main progenitor, the largest collapsed objects with most particles that enclosed in the final one. And if we go back to, say, some initial time, we only pick up one of many peaks that collapsed at this time. So if we look at redshift 15 for this object, the entire peak is collapsing, but a fairly large number of smaller peaks has already collapsed. And there is a most massive one that we pick as the main progenitor, but it's one of many, right? It becomes most massive on a given scale simply because we know that the only thing that affects collapse of different peaks is background cosmology, which is the same for all these peaks, and their initial delta. So it's a peak with the largest initial delta that had a head start just because it got lucky fluctuation up compared to all the other peaks of the same scale. And such peak became the largest one. They assembled most of the mass by a given redshift just because it was highest value. So the way we construct the mass assembly histories, we're actually picking the peaks on a given scale that corresponds to the mass that was grown by this redshift that had the largest initial amplitude. There is a way to account for this and to construct a density profile that accounts for this fact. So that we, at each particular time, will identify as a main progenitor a peak on a given scale that will have the largest amplitude. This clever idea is due to Dalal et al., and you can find details in this paper, or again in one of the background notebooks Actually, even in this notebook, it's duplicated. I just not show it to you, but if you're interested to go through the actual argument and how this profile derived mathematically, you can do so. But the idea is actually is simple to grasp. Well, maybe not so simple, but it's possible to grasp qualitatively without going into equations. The idea is that when we are considering collapse of a peak of a given scale that will result in a halo of a given mass at redshift 0, so we are constructing a mass accretion history of some object that will become the final mass of 10 to the 12. So it corresponds to some radius, Lagrangian radius of large R. And suppose this peak does have initial amplitude extrapolated to redshift 0 of 1.69, which guarantees that it will collapse by redshift 0. But at high redshifts, this peak is still evolving, still has not collapsed. But within this peak, there is lots of, when we consider scale R, some other R, within this peak, there could be a bunch of peaks on scale R because they are much smaller, and you can fit a lot of them within this peak of large radius R. In fact, the number of such small peaks that you can fit is just a ratio of radii cubed, the ratio of volumes, right? And it's possible, so then we, in simulations, we pick as the main progenitor collapsing at a given radius, so we can assume that that's what we're doing, the maximum delta that any of those n peaks would have. So in other words, we envision that this collapsing region that will eventually collapse into a large object has substructure, so it has a bunch of smaller peaks collapsing on scale R, small r, that have initial over densities that just reflect the Gaussian fluctuation, the Gaussian noise in the field, right? So they all have, all of these little sub-peaks have different, they all have the same radius, but they have different initial deltas, and those initial deltas have some PDF, but that PDF, and that PDF is actually Gaussian. So they were just sampling the Gaussian field that corresponds to the initial perturbations smooth on a given scale R. But as a main progenitor, we pick only one of them. We pick one that would reach the largest mass, would be most evolved by a given redshift, and that corresponds to the peak that has the largest initial amplitude. That turns a Gaussian statistic in so-called Supremum Statistics. It's also a very well-known thing that if you have a bunch of Gaussian numbers, n numbers, and you are interested only in the largest one of them, you can figure out what statistic, what the PDF of those largest values will be. It's called Supremum Statistics. It's something you can find in textbooks, and again, equations for this you can find for a Gaussian field in Dalal et al. Or in this notebook. But this is known, so we know what the PDF is. So in other words, we can figure out what the mean delta will be for the maximum of all the sub-peaks that are filling within this peak, within this large peak. Make sense? At least qualitatively. Supremum statistic of a Gaussian field is known, so that's qualitatively the answer for this. And we can compute what it is. And so the difference, if we do this, and again, this is computation that you can find in the notebook, the profile that you get for this is this, as opposed to the previous one that's shown by the dashed line. And the variance is with respect to the previous one. The variance around this peak is actually much smaller because the peaks, the maximum distributions, will have much smaller variations. Because Gaussian field does not allow you to go to very far into the weeds because it falls, the probability falls very quickly with the value. So this profile corresponds at every given scale. It corresponds to the maximum, the average of a maximum delta if you threw an n Gaussian numbers and pick a maximum of them, and you do it again and again and again, and then compute what is the average of that maximum value that I'm getting. It's an analytic formula for the Gaussian field, and this was used to compute this profile. In other words, the difference between these two profiles is that this profile on this qualitative level accounts for the presence of substructure inside this large peak that will collapse first and will be identified as the main progenitor of the halo. So let's take this profile and turn it into a mass assembly history. Here, as opposed to this flat profile, you can see that density is actually varying, right? So density does decrease with increasing radius, which for the collapse time will tell us that collapse times will be different for different shells, so the mass assembly history will be stratified in time. Right. So this is what we get. So this is just taking that profile, the Supremum profile, applying the spherical collapse model, and this is the mass assembly history that it predicts. Now this looks much better, I hope you agree, right, compared to the first model. We're still working with the spherical collapse model, so any deviations now, again, we can blame for either the collapse model, or maybe we're still not quite correct in figuring out what the initial density profile is from the Gaussian field. This is a much better guess now, which has this refinement for identifying the subpeaks. But any deviation now can be blamed on both, and in this case, I can tell you that the answer is that both are wrong at an roughly equal level. So now the spherical collapse model is wrong at a level that explains the discrepancy at high redshifts, and the profile is not quite correct at the outer regions that define how the mass assembly history looks like at late times for this model line. To see that it's true, what I just said is true, is we can look at we can go beyond the spherical collapse model and look at ellipsoidal collapse model. So instead of considering collapse of a sphere, we consider collapse of homogeneous ellipsoid. It's a problem that many people have worked on, but one of the definitive studies was Bond and Myers in '96, which did the numerical calculations for collapse of ellipsoids of different shapes, but homogeneous density inside. And these equations have to be solved numerically because we no longer have the simplification that the mass inside, the only thing that defines evolution is mass inside a radius. First of all, we have to consider evolution of 3 radii corresponding to 3 principal axes of ellipsoid. Then we also cannot assume that the mass outside is spherically symmetric, so we have forces that arise both from asymmetry of the perturbation and also from the presence of the tidal field that the given perturbation can fill, because non-spherical perturbation can now fill tidal fields from surrounding peaks. So instead of a simple equation like this for spherical collapse model, we have 3 equations for 3 principal axes, and in addition to gm over r squared term, we have a term which I will not write down, but just physically it corresponds to the fact that we're dealing with a non-spherical distribution now, but ellipsoidal distribution, and a term that describes the torque that surrounding peaks, which we are not considering, but they are present in the universe, that act on that ellipsoidal distribution, and they can create certain angular momentum, create certain torque, and angular momentum slows down the collapse. So that the term enters as negative. So actually, the net effect of both of these terms is to slow down the collapse. So compared to spherical collapse model, the ellipsoidal perturbations collapse slower, maybe as fast as spherical if ellipticity is small, but in general slower than the spherical perturbation of the same delta, right? For Gaussian field, we also know the statistics of these shapes. So what is the distribution of these principal axes, or the 2 parameters, ellipticity and prolacticity, that's defined relative to them, that also involve the perturbation amplitude. This was figured out in the 70s by Andrey and Chesmo and Tormin in 2001, they use these results to show that you can approximate the threshold for collapse. So instead of a spherical collapse delta that's equal to 1.69, you have this much more complicated expression that now depends on ellipticity and prolacticity. So in other words, the initial overdensity extrapolated linearly to a given time, whether it's enough to collapse or not, now depends on ellipticity of perturbation, which doesn't make sense, right? If perturbation is spherical and E is equal to P, this term becomes 0, it disappears, and we just end up with overdensity of spherical collapse. They also show that if we're interested just in most probable values, so this is, we can take a distribution of E and P, which is predicted by Darashkevich way back in 1970, and just sample it and determine the threshold for every single random realization. But if we're interested in most probable values, we can also come up with a much simpler expression that looks like this, where threshold for collapse of ellipsoidal perturbation is equal to the threshold for collapse of spherical perturbation modulated by this term. So it's a term that increases with increasing sigma, so it will increase towards smaller masses with the given parameters that can be figured out even from this basic statistics. We showed that in simulations, if we look at simulated halos, this actually works. So if we look at initial overdensities of halos that collapse in simulations of a given mass or a given corresponding initial RMS sigma, we do see that initial delta was not constant. Simulation results are shown by points here. And the line, the red dashed line here, shows the previous expression on the previous plot, whereas the blue dashed line shows the constant value predicted by spherical model. So at small sigmas or large masses, the two predictions are similar, but at low masses, this prediction the spherical collapse prediction underestimates the collapse over density. In other words, it's harder for typical perturbation of galaxy scale mass to collapse compared to spherical collapse prediction. Okay, so we can modify this model simply. So we can use the same model, but instead of using the spherical collapse over density, we can use this. Because if we're considering an object of a given final mass, we know what the sigma is, corresponding sigma is. We can take this formula predicted by the ellipsoidal collapse model and simply replace this critical over density for collapse predicted by spherical model by the corresponding values predicted by ellipsoidal collapse model, right? This is something we can do. And this is what you get for exactly the same profile as before, but using this threshold as opposed to this one. You can see that at high reaches, the line now goes close to median of the simulation results. At low reaches, we still have an issue. So it means that this issue is not part of spherical versus collapse, but at high reaches, you could see that the main reason the model was still discrepant at some level was the fact that spherical collapse model was too simple, too simplified. It turns out you can even figure out why the problem is at small reaches, is simply because when we were using this profile, we constrained the profile to have a particular over density at Lagrangian radius of the perturbation, but we didn't constrain anything what happens outside of the perturbation. A given perturbation on a given scale could be sitting right next to a big cluster and could actually be eaten by that cluster during evolution, and so never become an isolated halo of 10 to the 12 solar masses, but that's not taken into account. The actual halos that survive to redshift 0 at small galactic mass have profiles that are somewhat steeper than what's shown here for any average region. And this fact can also be taken into account because we can construct a conditional probability density, condition not just with a given delta at this radius, but also with a given slope at this radius. So we can use any number of conditions and still figure out what the corresponding profiles will be at the Gaussian field. And this is a solid line that you see here. So this is already kind of just playing with subtle things, but just to make a point that it's possible to refine this further and further, still maintaining this relative simplicity of this model, and get a result that fully describes numerical simulations. Now this model that now has ellipsoidal collapse threshold, but also constrains the slope of the perturbation to be a particular value that's close to what the actual slope should be. The main thing that I want you to remember from this is that the shape of this line is a consequence of collapse, either described by spherical model or by ellipsoidal collapse, but effectively what it does is it reflects the shape of initial delta profile. So what we're seeing in inverted form is the shape of delta versus enclosed in a given radius. This is the inner part of the profile, this is the outer part of the profile. But the shape of these mass assembly histories is defined by the shape of delta, initial profile of the perturbation. So these two regimes, the fast accretion regime and the slow accretion regime that we see in mass assembly history, correspond to the inner part of the profile of initial peak and the outer part of the profile of initial peak. Why is this important? Because we'll see that those two regimes will get imprinted into evolution of gas mass, will get imprinted in evolution of stellar mass of the galaxies that result from this model, from when galaxies are actually forming. So I'll leave you with takeaway points and take any questions that you guys may have. Yeah.
You say that some peaks.
Can you speak louder?
You say that some peaks that
Yeah.
They are only Gaussians.
Mm-hmm.
Why?
Because so when in this model, what we're doing, we're considering the initial field before it evolved to gravity. We assume that the initial field is Gaussian, right? So it means that any fluctuation on any scale is described by the Gaussian field. This is something I talked talked about yesterday, but let me reiterate this again. If we consider perturbations on a given scale R, the PDF of such perturbations, so I'll denote delta R because I consider perturbations that are enclosed within a given radius. They are always Gaussian, regardless of the scale. As long as I'm determining this for a Gaussian field using a linear filter, the PDF of the perturbations will be Gaussian. And this is sigma at this scale. Make sense?
Yes.
Okay. So then your question was about sub-peaks, right?
Yes.
And the question was why I can assume that they're Gaussian.
Why we assume they're only Gaussian?
So what's the alternative? So I tell you that if I consider perturbation, so I'm considering collapse of a perturbation on some large radius R. So this R corresponds to a Lagrangian radius that's set by the mass of the perturbation. And then inside of this perturbation, I try to account the fact that there are, we're dealing with a field that has perturbations on all scales, and I'm considering what will happen to perturbations on some other scale of small r, so which is smaller than r, right? And I'm interested in statistics of these perturbations. Are you asking why I'm assuming that delta of these perturbations will be Gaussian or not?
Is it possible that we take such a big R big that we have inside this sphere another non-Gaussian big?
It is possible, but then the assumption would be that in our cosmological model, the initial conditions would be non-Gaussian, right? In principle, it's possible to assume it becomes a structure formation model with non-Gaussian initial conditions.
Well, it's a part of this spherical curve we were talking about, yes?
No, here we're talking about the nature of initial perturbations. So the initial perturbations probably come from some process such as inflation, as Anatoly explained yesterday. And we don't fully understand what that process is. Of course, there is a theory of inflation, but we don't fully know that it's correct, right? But even within the theory of inflation, what it predicts for the properties of perturbation depends exactly on the potential of the inflaton field and how it evolved. So the generic predictions of inflation models is that the statistics of perturbations that result from inflation should be close to Gaussian. But there are inflation models that predict non-Gaussian initial conditions. In the models that we're considering, and the standard model for galaxy formation, for structure formation, is that perturbations are Gaussian. It's not that we cannot assume something else, but there is no, like using Occam's razor means do not introduce complexity unless you need to. It's not, non-Gaussianity is not introduced because there's no data that requires it. People have tried to do it and explore how different the evolution would be, and you find the differences in principle that could be detected observationally. But so far, all the data, most importantly the fluctuations of temperature in the CMB field, does not show us any evidence of non-Gaussianity. And so the simplest assumption that initial perturbations is Gaussian seems to be correct. Was that your question?
Yes.
Okay. So with these smaller subpeaks, essentially I'm assuming that this large peak is some Gaussian realization of a PDF on its own scale, R, big R, large R. And then when I consider statistics of small peaks, I consider each peak to be a random realization of a Gaussian field on the small scale. And then I'm taking a Supremum statistics. So I'm taking, okay, if I have one realization, I will pick a maximum delta, where deltas were distributed Gaussian, but I only pick the maximum. I use another realization and use the maximum of that. And then again, realization, another maximum. And then look at what the average maxima would be for different realizations. That average corresponds to so-called Supremum statistics of a Gaussian field, which is analytic, right? And that's for every R in the initial profile, I use that Supremum average instead of just whatever Gaussian field tells me. Because I'm envisioning that the big peak is filled with small peaks, that realizations of given Gaussian field.
More questions? No questions, thank you.